Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we're doing problem number 4.65. Problem statement says 5 liters of liquid N-hexane and 4 liters of liquid N-heptane are mixed and burned with 4,000 gram moles of air. Not all of the hydrocarbons are burned in the furnace, and both carbon monoxide and carbon dioxide are formed. If it is possible to do so without additional information, calculate the percent excess air supplied to the furnace. If more information is needed, state what it is and outline the calculation of the percent excess air. I've outlined the process here. That they were talking about. We have a certain amount of air going in, a certain amount of N-heptane and hexane. And we got a bunch of unknowns that I've highlighted in red. Okay. Then they didn't give us any information about the reactions, except to say that, there was not incomplete combustion, right? So there's 4 reactions that we need to account for. Okay. And let me just show you how to balance these equations. I've balanced these already, but let me just show you how to balance these really quick. So I'll go ahead and erase this one. So what you want to start with first is the carbon, and then you can do the hydrogen. Okay, so there's 6 carbons over here, so this needs to be a 6. Okay, then we do hydrogens. There's 14 over here, so there needs to be 7 of these, because 7 times 2 is 14. Okay. So then now we need to count up the oxygens on this side of the equation and then write down how many oxygens we need over here. So 7 in the water and 12 in the carbon dioxide. So 12 plus 7 is 19. Okay, so then over here there should be 19 oxygens. So 19 divided by 2, because there's 2 in this molecule, so 19 divided by 2 is 9.5. Okay, so that's how you balance those equations. You do the carbons first, and then you can do the hydrogens, and then you count up how many oxygens are over here, and then you balance the oxygens last. Okay, and if you really wanted to do it so that it was a real chemical reaction equation, you would multiply this whole thing by 2 in order to get rid of the 0.5. So then this would become 19, this would be 2, this would be 12, and that would be 14. Okay? So that's how you balance those. And you need to do that before you start using them, because these coefficients are important to do the extent of reaction and calculating how many waters you have at the end and things like that. Okay? Then we would need the hexane properties and the heptane properties, because they gave it to us in liters, right, in a volume. So we need to calculate what that is in moles if we're going to do reaction equations, right? Okay, so we write down what the densities are, and I have it in liters and grams because we're working in moles and liters. Okay, so we have this many moles going in of hexane, which I signified by writing a 6 here, sub 6, and heptane by writing a sub 7. So moles of heptane there. Okay. Oh, sorry, that's the molar mass. This is the number of moles. Then you go ahead and use that in order to calculate what the number of moles are using this information. Okay. Okay, so now we can do the degree of freedom analysis, right? So our degree of freedom analysis, we have 8 unknowns. Just count all those up right there. How many independent atomic equations do we have? Well, we have nitrogen, carbon, oxygen, and hydrogen. Okay, so that's 4 balances there. And then we have one process specification, which is that the sum of the mole fractions need to sum to 1. Okay, so the sum of these need to equal 1. Okay, so then that equals 3 degrees of freedom. So there's not enough information to perform this calculation in order to calculate what all of these unknowns are. Okay, so we need more information that can help us describe what the extent of reaction is for at least 3 of the equations, because we have 3 degrees of freedom. Okay, but this is how we would solve the problem if we had the extent reaction or some sort of component information. Maybe we know what a couple of these components are, and then that could also help. If we knew what 3 of those components were, we could also calculate what the extent of reaction is as well. Okay, so we start off by doing our nitrogen balance, which we do have some information for, but we don't know what this is. So we can't calculate what this is either, right? But we do have we have the most information about nitrogen because it's not participating in the chemical reaction. Then we can do our oxygen balance. So you say, okay, this much oxygen going in. This is oxygen element, not like we did with nitrogen. We did just a component balance. This is an elemental analysis, okay? So there's a component of 2 there because 2 oxygens for every oxygen molecule going in. Then we have 1 mole for every carbon monoxide, and 2 for every carbon dioxide, and 1 for every water, and 2 for every oxygen that comes out on the other side. Okay? Then for hydrogen balance, we have 14 going in with the hexane and 16 going in with the heptane. Then we have 14 going out with the unburned hexane, 16 with the unburned heptane, and then we have a certain amount of water, and there's 2 for every water. Okay. Same thing with carbon. There's 6 going in with the hexane, 7 going in with the heptane. Same going out the other side, and then there's a certain amount that was burned, and so there's 1 for every carbon monoxide and 1 for every carbon dioxide. Okay. Then we do our extent of reactions balances. Okay. Okay, so then we do how much carbon monoxide we have at the end. It depends on the extent of reaction of these 2 equations. And then the same thing for the carbon dioxide. We have a certain amount of carbon dioxide that's formed, and it's based on the extent of reaction of these 2 equations. And then with the water, same thing, except for it's based on all 4 of the equations. And then same thing for the oxygen, except for this is a product, or a reactant, right? So you start off with a certain amount, and then you lose a certain amount based on the extent of the reactions, right? So that's how you calculate. This gives us all of the equations that we would need to solve for all of the unknowns, right? This gives us enough information if we know just 3 more of the variables or have 3 more pieces of information. So you'd use a combination of all of these equations in order to solve for the unknown variables. And that is it for problem number 4.65. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.